we're not always sure exactly where the points of curvature and points of tangency are going to show up on our roadway. And I can say from experience, if you've been around asphalt paving, that centerline joint that we're trying to say is the middle of the road, or even the edges of the road, which we want to find the midpoint between them, those things aren't perfect. So we can measure much more precisely and place things much more accurately with surveying and computational methods than you can with the controls of an asphalt paver. In reality, what we laid out as a circular curve, here you can see edges of pavement, it's intended to be a circular curve, may not be very circular, or there may be sufficient variation in the field that it's hard to determine just what kind of arc is that. If you deal with railroad curves, you can get some real surprises. Not only do they have circular curves, but they have spirals, and if it's an old railroad, well, those tracks get yanked around all kinds of different directions. I've got a series of blue dots where, of course, I had my side shots. And those blue dots may be all you see on the screen of your workstation if you're doing coordinate geometry, graphical coordinate geometry. And really, those represent the center line of that highway. Well, how is it that I can find where that curve really is? I know I've got shots that fit the wandering center line of that, so I've got to come up with a way to do a pretty good fit. A circular curve is merely a mathematically defined transition between two tangents. So I think you can see I've got a bunch of lines, or a bunch of points in a line that define a tangent. So I'm going to go ahead and draw some lines here. In the real world, it requires a little bit of trial and error. And I'm going to pick a point there and come up with what I believe. There you can see that one is probably down in the curve. I'm going to go ahead and select that guy there. And it appears that all those points fall on a tangent. I'm going to come down here and I'm going to see how that fits. That doesn't seem to fit so good. That seems to fit okay, at least on that point. And understand, of course, I'm giving you an idealized scenario here. It's rarely this neat, but this is the thought process we apply. Okay, I think we need to be about there. And so what you see here is I have three tangents. And those tangents will form the basis for these circular curves. Now I've turned off all my spots, so now all I have are those tangents. So I need to do a little more labeling, and this time I'm going to label the endpoints of these lines, because it is the coordinates that I use here that become the basis for my computations. I need to intersect this line and this line. And I need to intersect this line and this line. That will create what we call a point of intersection, which is an essential part of a horizontal curve. Let's go back to your orange book for a second. Let's skip down to intersection computations. This is on page 61. When we need to computationally intersect two lines, we have a couple ways of doing it. Three types of intersections. One is direction, and we're going to use a sine law to do that computation. Then we have distance, which we can use the cosine law for, and then direction, distance. We can use the sine law as well. And you can see sine law and cosine law spelled out here, and I know you've used them in your math classes to date. But a direction intersection is one in which we know the direction of a line, and then we know the direction of another line. When we start this, we know if you extend those lines, they can intersect, but we want to know what the coordinate is at that point of intersection. In the process of doing this, we have to take a little bit of a roundabout approach. If you're trying to find the coordinate at point C, what you must first do, like step 1 here says, you have to inverse from point A to point B. Then you'll simply be using the computed azimuth from A to B, along with the 2 known azimuths, to compute the interior angles of this triangle. Once you know all 3 interior angles, then you would know the interior angle here at C, and then you also know this distance from A to B. Once you have an angle and you know the length of the opposite side, then you can come up with the opposite side that goes with another known angle. And that's effectively what you're doing. If we get back to our tangents on our highway, what we effectively want to do is find the intersection point expressed in coordinates of these 2 lines. Well, the effect is to come up with that point there. And here I'm making it easy by doing it in CAD. But I need that point because this is what we call a point of intersection. This point of intersection helps us define how a curve fits in the real world. So if I go ahead and I create the intersection of these, then the points that I computed from before still exist. They are on these lines. So you could say this point of intersection and this point of intersection form a line that is collinear with, or really the extension of, the line defined by this point and this point. How does this relate to curves? Well, in this case, you can look in here and see that, yeah, those curves are coming in, the spots on my curves are arcing through there. But really, how does this fit? And more specifically, where does the curve start and the tangent end? That's the question we raised earlier. Well, let's say in my scenario here, I've discovered that the curve that was created, that I have mapped, was originally built here with a radius of 1,000 feet. Well, I'm going to shortcut this, and I'm going to put that curve back in, and I'm going to tell it, see how well that fits, and I find out that yes, indeed, that seems to fit pretty well, doesn't it? Okay. And over here, it was supposed to be a 2,000-foot curve when it was originally constructed. Let's see if it still works out that way. Seems to be a pretty good fit. Let's go ahead and place a symbol at the beginning and end of each curve. When you're out in the field and you're doing a survey, you're standing out in the middle of this highway dodging traffic, and you're trying to figure out, now, where does the curve start and end? When you are right about in this area, it's going to be very, very difficult, especially given the variation in centerline joints and edges of pavement, to find exactly where this little point is, where you go from tangent to curve. So you've done your best and gone out there and guessed, and the blue dot may recommend what you guessed at. Okay? Same thing here. Not a bad guess, but is it right where it needs to be? No, not exactly. But it's by using the intersection tool, part of coordinate geometry, we can find the point of intersection. And then some of the things you're going to learn about circular curves will put this in even better perspective. We can say that the distance from the point of intersection up here where the tangents meet back to the PC and back to the PT, that is symmetrical. So you'll see how this fits together. Well, let's consider some more applications of inverse. One of the things then I would want to know is, all right, I guessed at this location for the end of that curve, and I guessed at the end of this curve. So geometrically, what is the distance between the two? Well, I'm going to simply use a CAD tool to find out, but I can find the distance and the direction by doing a simple inverse computation, and that's what I have here. 749.78, 282.4730 being my direction. So inverse is something we use all the time. I can't tell you how important understanding how to inverse is. The more you can do it by hand, the better you can make sense of what you get from data collection methods. Inverse is the backbone of computations in not only side shot, but it is also the backbone of computations for intersection problems. Every intersection problem starts out with inverse in it. This first one, direction, direction. First thing you're going to do is inverse. If we scroll down, let's take a look at distance, distance. The very first thing you're going to do is inverse. And then we go down to distance, direction. And the very first thing you're going to do is inverse. So it's very, very important that you get this down. On page 57, there's a computation called perpendicular offset computation. This is another application of inversing. And simply it is finding out what is the offset left or right of some tangent line. Not only the offset, but the station along that line. And let me give you a real-world application of how I use this, especially when I'm doing boundary surveys. What I want you to consider here is 4 streets, and the parallel lines here representing the streets would be right-of-way lines. That is the property line that separates private property from public property. And the block that you see here is the type of lot and block layout that was common up through the early part of the 20th century. It was fairly common that lots were 66 feet wide or one chain wide, and maybe some even number of feet deep. I have seen this 66 by 124 foot dimension combination in several places. It was also fairly common to have an alley that is 1 rod wide, that is 16.5 feet. Let's say I have to do a boundary survey out here, and I am reestablishing the north line of this alley. The south line, I have found a whole bunch of property pins, what appear to be property pins, and ideally what I'd like to do is simply measure over from the right ones and get the property corners in the right places. However, before I do that, I have to find out if they do indeed line up and form the straight line that they're intended to be. As part of my evaluation of the existing conditions, I have to see if these points are collinear. That is, if they all fall on the same line. So what I'm going to do in this scenario is do a perpendicular offset computation. And what I have to do is select a line, a pair of points that define a line, and then compute the relative positions of the other points against that line. So in this case, what I've done is simply say I'm going to hold the position of the west end of the alley and hold the position of the pin at the east end of the alley, and I'm going to compare the others. Well, what I may find is that with the perpendicular offset calculation, I find that this first one is 86 hundredths north of the line, and this one's 59 hundredths south of the line. Well, north of the line. This one is a half a foot south of the line. This one is just a mere 9 hundredths south of the line. This one fits perfectly. And then here's another one that's 23 hundredths north, and one that's a mere 8 hundredths north. Well, what that may tell me is that I may want to go ahead and trust the points that I have held and use those to define the straight line that I need. Whereas if I simply said, okay, I'm going to reset points at these locations, if I'm simply going to reset points at these locations, in order to get them in the right place, I couldn't simply measure 16.5 feet north from this one. I would need to measure from the line that I have accepted. That is, the straight line that goes from this end to this end. Because now I have found that these points that I have measured and established coordinates for fall either right or left of the line. Alright, so that's a very important analysis tool that I use heavily in evaluating existing conditions in the field as a land surveyor. Like we said, this is an application of inverse calculations. In fact, to do this one, we've got two inverses. We have to inverse between point 1 and point 2 first, and then we have to inverse between point 1 and point 3. So therefore, we'll have the direction of two lines. One line is the basis for our analysis, and the other one is simply an intermediate step. So if I want to find out how far 3 is left or right of line 1, 2, I've got to do two inverses. I've given you a set of instructions followed by a worked problem complete with the solution. And notice that the solution includes a left or right type of result in the answer. Well, that makes sense given what we're describing here, because if my direction is considered from point 1 to point 2, then you can see by this drawing, point 3 is on the left side. If I reverse my reference line going from 2 to 1, then point 3 is on the right side. So that's going to be very important that you pay close attention to the direction of your analysis.